So how do I figure out the variance of this P? Yes?
Since the indicator functions are independent, the variables are independent, then the variance of the sum is the sum of the variances.
So you have used a very interesting property of variance, right? Let's actually derive it over here. So do we all know what variance is? So a variance of a random variable, let's say P, is equal to the expectation of P squared minus expectation of P squared, right? Okay, and if P is composed of, let's say, if P is composed of is the sum of two independent quantities. So let's say if P is equal to P1 plus P2, and being independent means the expectation of P1 times P2 is equal to the product of expectations, right? And that gives us a way to simplify the variance of P. So when we plug this summation in, what we get is the expectation of P1 squared plus 2 P1 P2 plus P2 squared, right? Minus expectation of P1 plus expectation of P2 squared, right? So this is basically plugging in the definition of P equal to P1 plus P2. So here is an opportunity to use the linearity of the expectation to break it apart into three expectations. And for the middle expectation, we can split that expectation into the product of expectations. So what we get is expectation of P1 squared plus 2 times the product of expectations, and then plus expectation of P2 squared. And then here, the minus part, let's also break it apart. The first term is expectation of P1 squared, which is outside the expectation, minus 2 expectation of P1, expectation of P2, which exactly cancels what's from the first term, and then minus expectation of P2 squared, right? So what we realize is the middle term gets cancelled, and this combines to be the variance of P1, and this combines to the variance of P2. So just like what has been pointed out, the variance of the sum of two independent random variables, or actually what's required is just this, right? Which is actually weaker than independent. Two variables that satisfy this are called uncorrelated, right? So independence implies uncorrelated. So if I have independent variables, this is definitely true, and I only need uncorrelated variables to have the variance of the sum equal to the sum of the variance. Now you can apply this procedure repeatedly for the summation of n random variables. All of them are independent. You can first split it into the first one and the summation of all the rest, right? And then you can split the summation of all of the rest into the second one and all of the rest, etc. You can apply this for 999,999 times. What you get is the variance of P is going to be the summation of the variance of all these million individual constituents. So variance of P is going to be the summation of I goes from 1 to n, the variance of, let's see what it is. Don't forget the 1 over n times this indicator function. xi squared plus yi squared greater than 1.99. Right? Now the rest is to figure out what the variance is according to what? Well, the definition of variance. All right. So the definition of variance is the expectation of p squared, which is, what is p, right? P is 1 over n times something that is either 1 or 0. So let's write it down. Oh, again, like, because all of these x and y's are identically distributed, this summation is just multiplied by n, right? Okay. And also, if I scale a variable by 1 over n, how much does that do to its variance? Yes, it's n squared, because look at the definition. So if I scale p by 1 over n, this term is scaled by 1 over n squared. Again, this term, because there is also a square, both terms in the definition of variance is scaled by 1 over n squared. So we had n, which is from the summation, and we had 1 over n squared from this 1 over n. So they don't cancel, like in the expectation, right? They don't cancel. The more n I have, the less the variance is, right? That's the benefit of using more samples in the Monte Carlo method. And then I have a variance of identity function. So not identity function, but indicator function. So what's the variance of an indicator function? Let's use the definition, right? So for indicator function, because the value can either be 0 or 1. I mean, the random variable can either be 0 or 1. So the indicator function square is itself, right? I mean, if the indicator function is 0, its square is also 0. If it's 1, it's also 1. So the square is just the function itself. Okay, let's write it down. So, and then the expectation of that indicator function is, of course, the probability of that event happening, right? Okay. And then I have to minus on the event happening probability squared. So that's going to be the variance of my Monte Carlo method. Or if this is the true answer, let's write it as a small p. The variance can be written as 1 over n p minus p squared. So that's my expected variance of my Monte Carlo result.